Okay, last time in the last video they gave us a point on a line and then they gave us a vector and they said, alright, go parameterize the line. Now they're going to give us 2 points and they're going to say, go parameterize the line. Okay, so the difference is 2 points, no vector, whereas last time we had 1 point, 1 vector. Okay, so let's see here. We'll just call this line L. Okay. And just based on everything, okay, we know what we know the points here. Okay, 6, 4, 2. I'm not going to rewrite them, but we're actually going to go ahead and we're going to use point X, and we're going to call it X, Y, Z. Okay, we're going to do that again. So from there off, we can make the claim that vector P1, P2 is parallel to P1, X, which is also parallel to L1. Okay, sounds a little crazy because they're all stacked on top of each other, but I mean, they truly are parallel. I mean, you know, just because they're on top of each other doesn't mean they're not parallel. Okay, so let's go ahead and let's define P1, P2. Okay, so let's define that as a vector. So it's going to be what, 2 minus 6. 2 minus 6, that's negative 4. 1 minus 4, that's negative 3. And 1 minus 2, that's negative 1. Okay? And let's see here. Px is equal to x minus 6. Actually, let me write it down here because I think I'm going to run out of room if I do it down there. Okay, so that's what? That's x minus 6. It's y minus 4, z minus 2. Okay? So, let's see here. We already made the claim that px and P1's P2 were parallel to each other, so the only thing we got to do now is come up with some magic number, that magic number being t, and we'll multiply t by vector P1, P2, and that's going to be what makes these things equal. Okay, so this is just some scalar multiple that's going to ensure that everything's equal. Okay, so Px is now equal to P1, P2, which all I'm going to do is distribute the t in here. So if I want to go ahead and do this, that's all I got to do is I got to put the t in. Okay, so I'm not going to rewrite it because that would be redundant. Okay, that'd be redundant. It would be redundant. It would be redundant. Okay, I don't know if you guys got that joke that I just said, but oh well. Okay, so there we are. So now I can go ahead and I can make the claim that we have some parametric equations. Negative t equals z minus 2. Okay, I guess it's kind of customary, you know, we can go ahead and solve. We can solve for t, I guess, if we want. Let me see if I got a clean piece of paper. Yes, I do. I do have that. It's the hardest part, is just picking these things up. I mean, I wanted to make everything look good for everyone, but that's what happens. So let's see here. X is going to be equal to negative 4t plus 6. Y is going to be equal to negative 3t plus 4. And Z is equal to negative t plus 2. Did it all fit on there? So there you go. There are your parametric equations for L1. Okay? So do we see what's going on there? Do we like it? We found I think the kind of the trick is we kind of slipped this X point in here, and just like the last time, if you're stuck on a problem like this and couldn't really figure it out and didn't understand why, it's just a matter of defining a line, in terms of variables and in terms of constants. Okay, so that's all we did. Okay, so I hope you see how it worked, and I hope that made sense, how I went through there, how these are equal, and so on. Okay, because it's really a key element of what's to come, and that's vector calculus. Okay, so again, thanks for watching my videos. I've been I've been up late. My dog's been drinking out of the toilet, and then I forgot to put water in her bowl, so that explains why. And all sorts of stuff's going on, so oh well. So thank you for watching. All right, see you next.